Hello student, welcome. In this video, we will solve problems on the topic the method of least squares. As you can see here, for most of the problems, almost all problems, the list of the answer options as a multiple choice, including the correct answer, and in some cases just the correct answer is provided in the document in the file that is made available to you either through your LMS or in YouTube description. The reason for that is in the video, I will solve some of the problems with explanation and you will be taking notes, with for that. But you also have the file with you downloaded or printed and you should complete the rest of the problems on your own. The answers are provided so that you can check your work as a standard reference. Okay, keep that in mind, not just for this lesson and this problems, but for all the problem sets that we will solve in this course. Okay, let us begin. In the first question, the word regression line is used, and that reminds me to quickly give you a historical account here. Why is it called the regression line? We studied it as the least square feet line. So it seems in 1800s, there was a scientist. My apologies, I don't have the name off top of my head. The scientist in England, Britain, I believe. Okay, he was studying the relation, the population, the height of the people, and he found that the parents who are either very tall or very short tended to have offsprings, their children, whose heights would be more closer to the um, average height of the population. Okay, so he called this a regression to mediocrity. Here, mediocrity, not in a negative connotation, in the sense of the mean population, the average population. Okay, the average height of the population. So and that line was the line that was fitting the data in the best way, right? Hence the historical connection between the terms. And today we call it the regression line, and this whole method is also called regression analysis, as you might have heard or seen if you're reading some literature on this or watching some other videos for understanding. Okay? And let us now solve this problem. The solution of the problem is going to be routine. Okay, I want to work out one problem fully with you, at least not one, maybe a couple of problems. You do the same, and as you are doing it, try to um, have the process imprinted in your understanding. Okay, what are the things that we need to write in this table? X, Y, remember the formula. Okay, if you sometimes wonder, what should go into the table, recall the formula. The slope is n times sum of xy minus, this is the sum of products of x and y, right? Then I remember the next term will be the product of sum of x and sum of y in the numerator. In the denominator, again, n times sum of squares of x minus sum of x squared. There is that connection between the terms in the numerator and terms in the denominator, right? Sum of xy, the product xy minus products of the sum of x and sum of y. In the denominator, sum of squares of x times n minus sum of x whole square. Similarly, the formula for b, you might remember again, is okay. Now, and if you tend to forget, there is a quick way to remember it. Remember the line that we are drawing is y equals mx plus b, right? That is the slope intercept form. And what is b here? B is y minus mx. So that is what is the formula for b here also. But except it's not just one point y, x comma y. There is a set of points here. So you would be doing summation y minus m summation x. But when you add so many things, you need to average them out, right? Divide by, okay? And that formula I wrote there so that you will also compute anyway, but also it tells you what should go into the table, xy and x square. That's all we need, okay? And at the bottom of the table, let me already do it. You can draw this line here. So you can write the sum, all the sums will go to the last row there, okay? Which means in the space in between, we need to write the points. X is 0, y is 4. The values come from the data. X is 1, y is 5. I guess I need to write a little small. X is 4, y is 11. X is 5, y is 10. Okay. Add x. Sum of all x's is going to be 10. Sum of y's is going to be 33. Then you multiply 0 times 4, 1 times 5, 4 times 11, 5 times 13. Take the sum, 114, and x squared. So that will be 0, 1, 16, 25. Take the sum, 42. Okay. Hence, now I will continue this down here. When I plug in, m will be, by the way, n in this case, I will write here separately. The value of n here is the number of data points. There are 4 data points. So n is 4. Okay. And let us do that here. 4 times summation of xy was 114 minus summation x summation y, 10 times 33 divided by 4 times 42 minus 10 squared, sum of x squared. Okay, that of course you put it in a calculator. So as you can see, when I type this in a calculator and I wanted to show you here, so you will not make a common mistake. Use the Note the use of parentheses. Okay, and sum xy minus sum x sum y is the numerator. You have to have the whole thing in parentheses. You don't need more parentheses inside because multiplication takes precedence over addition and subtraction, right? So that takes happens automatically. If that whole thing is in the parentheses, then that will be evaluated as a single quantity in the numerator, right? And then divided by, and the rest of the expression is denominator, so that should also go in another parenthesis. If you miss some of these, your answer should be incorrect. Okay, keep that in mind. Let us hit that now. 1.853. Okay, approximately. Let me use approximately 1.853. Okay, so what do I see here? 1.85 in the first option and the fourth option. So it's one of them. The answer we have here is E. Okay, let's see. It should be the fourth one. And how do I do that next? I need to find the value of b. Okay, continuing the computation of b down here, that would be sum of y, which is 33 minus m is what we just computed. Okay, now here's the thing. I said use the exact value for m in my earlier video, if you might remember. uh, but in this case, depending on how good the calculator you are using, if you are able to get a fraction on the calculator, see, you can convert a decimal to a fraction in some calculators. Okay, learn how to do that. There would be some key on the calculator which has this like a over b or c over d kind of notation. Okay, something similar to that, which will basically convert the decimal to fraction if it is possible. Okay, in this case it is. In that case, you can do that and use the fraction value here, which would be the exact value of m, so that your error in b is minimized. Otherwise, use more decimals than what we are writing here. Now, the slope is 1.85 as it is used in the answer options, but we will use more decimals, not even 853. Even that was a rounding off, right? Let's go back and see. It was 85294. Okay, so my recommendation would be use the value of m as 1.85294 or better accuracy. Okay, and that was m times summation of x, which is 10, divided by, of course, the number of data points, which is 4. Okay, so again, use the parenthesis accurately, appropriately, and that gives you 3.61775. Okay, so approximately 3.6162, which is the option here. Okay, all right. And as I was saying, options for you to practice, you can look at the second problem here, which is exact same problem with 4 points. Please do practice, and the answer is given for you here, so you can check it. Okay, the next problem. Some approximate values of a particular index are shown in the table. Okay, and find the equation of associated round line and all of that. Okay, and the logic is very similar again. Okay, these are index values, the years are x values, and the index values are the y values. So you are going to create the table with your points x and y as when x is 0, y is 50, when x is 2, y is 100, and when x is 4, y is 250. Okay, so one thing I want you to notice here is, okay, when x is like getting twice, double here, the y values are not exactly twice, right? Otherwise, it would have been easy to write the equation. Okay. But there seems to be not an exactly a linear relation, at least even with these 3 points. So you would have to find a line that tries to fit in these 3 points. Okay, 0, 50 is, let's say, here, and 200 is somewhere here, and 250 would be somewhere there. Now that would not go into a straight line. So what would you try to do? You try to find a line that will fit in. Okay, that's the goal here. And what is the question asking? Project the value in year 3. This is year 2 and year 4. Year 3 would have been in between, and that would have been somewhere here, right? So our goal in this problem is to predict that value. Okay, let us do this work. As usual, we are going to compute xy and then x square, and we are going to take the sums. Okay, let's first multiply 0 here, 200 here, 1000 here, and x square x, that's 0, 4 and 16. All the sums will go in the lower row here. I'm going to write next on this side for simplicity. Okay, sum x is going to be 6, sum of y is going to be 400, and sum of xy is going to be 1200, and sum of x squared is going to be 20. And in this case there are only 3 data points, so the value of n is 3. Okay, now use them in the formula. Your m is n sum xy minus sum x sum y over n sum x squared minus sum x whole squared. So what does that give you? That is 3 times 1200 minus 6 times 400 all divided by 3 times 20 minus 6 squared. Okay, that is 3600 minus 2400. 1200 divided by 60 minus 36, 24. 1200 divided by 24 is clearly 50. Okay, so m is 50 and b will be, wow, is it going to be a straight line? I might have misspoken. Let's see. Okay, I don't know if it is going to be an exact straight line. Let us see. B is given by formula as sum y minus m sum x y minus mx, right, divided by n, and that if you plug in here, I'm going to go down here. Okay, summation y, sum y is 400 minus m is 50, sum of x is 6 divided by 3. Okay, 400 minus 300, 100 divided by 3. The value of b is 100 divided by 3. So your regression line, I'm going to write on top here. Okay, is y equals 50x plus 100 divided by 3. So in the year 3, y of 3 is, now you are using this for prediction. So I'm saying approximately. Okay, at least that is the predicted value. Now, okay, sorry. Let me use the equality here, but we will keep in our mind that this is the predicted value, may not be the exact value. Okay. When x is 3, we get 150. 50 times 3 plus 100 divided by 3, which is 33.33. So when you round up, 183.33. Okay, that's 183.33. The answer is B. Right. So here we did one more step than just finding the regression line. Once you have the regression line, you can plug in the different values of x or y, depending on what you need, in order to make future predictions. Okay. Mhm. You could ask the question like, when will the index be this? That would be like, given y, you have to find x, the year, or you could give the year. In this year, what would be the y value? And one more thing we did here, which is I said earlier that we use it for prediction. Sorry. So the prediction does not have to be necessarily about future time, actually, as we see in this problem. Um, you can also try to predict the missing data. That is another important application, or an application of this concept. Okay. Suppose you had a bunch of data available on a certain topic, like the case of index here, and the data point for a particular year was missing, right? Or let's say, you knew the, um, if you are doing a study, like you knew the mm, height and weight of like certain number of people, and let's say, for a certain, for some people, the data was partially missing, like either you didn't have the height or you didn't have the weight. What would you do? You'd find this line, and once you find this line, you can, for the best fit line, for whichever data is partially missing, you can find y if x is known or x if y is known by using the least squares line or the regression lines equation. Okay. All right. Moving on to the next problem. I tried to avoid as much as possible, but for some reason I just slipped this. That turns out the next question is first line got printed here. Okay, um, please read it. In 2004, the Texas Bureau of Economics Geology published a study on the economic impact of using carbon dioxide enhanced oil recovery technology. Okay, and what did they find here? The table gives approximate number of jobs for citizens that would be created at various levels of recovery. Okay, so there are two things here. The levels of recovery and the number of jobs created in millions. Okay, 20%, 40%, 80%, 100%, 3 million, 6 million, 9 million, 15 million. It seemed to be going linearly, actually. Oh no, not exactly linearly. I was wrong. Okay. 3, 6, and 9 was linear here, but that was when the recovery percentage was doubling, right? So it's the correlation is not exactly linear. So we'll try to find a line that fits it. Okay. Find the equation of the regression line and use the line to estimate the number of jobs that would be created at 43% recovery. See, that is what I was saying about and the application of this concept. Okay. And I think I'm going to leave it to you. Like the process is routine. Okay. By now, there's only one topic, only one concept here. So make the table. You have the x values, you have y values, do the calculation, find m, put in here, find b, plug in here. And for 43% recovery, you are going to plug in the 43 for x. Once you have the equation, plug in x equals 43 and you get your y. That would be your second answer here. Okay. And finally, there's one last problem here, which is about soybean production. function of cultivated area. Okay, how much area was cultivated? That's given here in millions of acres, and the amount of soybean that was produced again in millions of tons given here. So again, it looks like, you double the area doesn't give you twice the amount of production. Okay, there is some, different type of relation. What could be that? If you are cultivating a larger area, maybe your, the way you do the irrigation, the way you distribute the mm, nutrition, right? What you put in for the plants to grow, and just the management of it. So many things change, right? If you cultivate, let's say, in a larger land than a smaller land. So it's not always going to be one, like, linear relation. I cultivate on twice the amount of land and my production will be twice as much. That will work probably on our garden or small scale, where resources and are really not the main concern, but on large scales things differ. See, this is the real science, okay? Real world application, right? And we cannot just assume linearity all the time. So you need the square feet line. Again, the answer options are there and the answer is there. Please request you to solve this also on your own. Okay, I will pause this video. I will see you in the next lesson.